Okay, let's continue with chapter 6 in the textbook of Cengel and Ghajar. Chapter 6 is on the fundamentals of convection. We've already, in the previous chapter, looked at transient heat conduction. Now, in this textbook so far, we've looked at the boundary layer, the velocity boundary layer, and the thermal boundary layer. And I've showed to you that they are very similar. And specifically, the Prandtl number actually tells us the ratio of the velocity boundary layer to the thermal boundary layer. And we've looked at three different scenarios of the Prandtl number. The Prandtl number equal to 1 means that the velocity boundary layer is the same thickness as the thermal boundary layer. And then we've got the other two cases of Prandtl numbers larger than 1 and Prandtl numbers smaller than 1. What we're going to do today is the last part of this chapter, paragraph 6.11, the analogy between momentum and heat transfer. And it is my view that this is something that is underestimated in terms of how important it actually is in the field of heat transfer. So normally with forced convection heat transfer that we're going to do in the next few paragraphs, this paragraph we look at the fundamentals of it. The next, in this chapter, in the next chapter we're going to look at forced convection of external flow. The chapter after that, internal forced convection, another chapter on natural convection, and then only then we're going to get to heat exchangers, the really practical application of heat transfer. And in all four of these chapters, you will see that in forced convection there are normally two things which are very important. The first one is the friction coefficient, and the other one is the Nusselt number. Why do we need the friction coefficient, or why is that important? Because if we have it, we can determine the pressure drop. And the pressure drop is important because that determines the external power which is being required by fan or a pump. So it is something that we pay for. So the power requirements. While with heat transfer is about the heat, the Nusselt number is about the heat transfer. How much heat will be transferred, and or if we know how much heat we want to transfer, how much surface area we need at a specific temperature difference. Now, there are a few paragraphs before 6.11 which you've already also done in fluid mechanics. And I'm just going to quickly jump to that, so it's not going to be clear to you exactly where it comes from, but you have done it in fluid mechanics, and it is actually the momentum equation for a flat plate, and it looks like this: u du dx plus v du dy is equal to 1 divided by the Reynolds number based on its characteristic length, multiplied by partial d2 u dy square minus dp dx. Okay. So that's equation 6.65. Now this is not exactly how the equation looks like. What has happened in the previous paragraph is that all this has been non-dimensionalized. And that is what the star is for. All non-dimensionalized. The detail is not important now. Then equation 6.66 is the energy equation, and the energy equation looks like this: u multiplied by dt dx plus v multiplied by dt dy is equal 1 divided by the Reynolds number, Prandtl number, partial d2t dy square. And again, this equation has been non-dimensionalized. So the velocity is the non-dimensionalized velocity, and the same with the temperatures, just like in the previous equation. Something like that. Now, if you look at these two equations, they sort of look the same. If we now go and look at the cases where the PDX is equal to 0, and that is an assumption that is being made for a flat plate, if you've got flow over a flat plate like that, then normally it is quite good to say the PDX is equal to 0. And if you now also make the assumption that the Prandtl number is equal to 1, and if you look back at these two equations, I'm going to remove this Prandtl number. So if it is equal to 1, and this equation disappears, what do you see? You see that the two equations look the same. And what it actually tells us is that nature tells us that what happens with a pressure drop, the same is going to happen with a heat transfer. Okay. I'm going to jump a few steps. The details are in your textbook. But the very important thing is it can now be proved that CFX, the local skin friction coefficient, multiplied by the Reynolds number divided by 2 is equal to the Nusselt number X, the local Nusselt number. And this is called the Reynolds analogy. The Reynolds analogy, a very important equation, but not appreciated enough by, I think, many people. Reynolds analogy, however, take note, it is valid for Prandtl number equal to 1 and for a flat plate. Now, what does this equation tell us? It tells us, as I've mentioned previously, that if we look at the momentum, if the momentum in terms of the pressure drop and all the forces is going to increase, then the same is going to happen with a heat transfer. Now, this is the first simple type of derivation that can be derived from this equation. It is a little bit limited because of the fact that the Prandtl number is only valid for fluids with a Prandtl number equal to 1. And there are not many fluids with this Prandtl number. Air is about a Prandtl number of 0.7, so it is quite close. You can use it as a first approximation, but this equation can be refined to the following equation. Before we do that, we first need to define what is called the Stanton number. Stanton number, and the Stanton number is also a non-dimensionalized heat transfer coefficient, and it is equal to the heat transfer coefficient divided by the density, the Cp, and the velocity. It can be written as the Nusselt number divided by the Reynolds number and the Prandtl number to the third, and it is also known as the J factor. The J factor, H to indicate the heat transfer J factor. From this, it can be shown that CFX, the local skin friction coefficient multiplied by Reynolds L divided by the 2, is equal to Nusselt X, Prandtl to a third, minus a third, and take a note here, look at this and that. Okay, so it's the same equation. The Prandtl number has just worked into this correlation, and the result is that you can now get that the skin friction value at a point X is equal to 0.664 Reynolds X to the minus a half, and or the Nusselt number, the local Nusselt number, is equal to 0.332 multiplied by Prandtl to the third multiplied by Reynolds X to a half. Or, in more general, CFX multiplied by Reynolds divided by 2 is equal Nusselt to Nusselt x Prandtl to the minus third. I've already written that down, sorry. Or you can write it as CFX divided by 2 is equal to the Stanton number x Prandtl to the 2/3 is equal to the J factor. And these two equations are now called the Chilton-Colburn analogy. And they are valid for Prandtl numbers for a wider range of Prandtl numbers, which includes values of larger than 0.6 and smaller than 60. And that actually includes most fluids and all gases. Again, this equation, you have to be very careful in terms of its application. Go and look at the fine print. You'll see that it is only valid for turbulent flow. Also, the PDX should be equal to, is not equal to 0, and it is limited to a flat plate. Okay? So two equations, the Reynolds analogy, valid for Prandtl number of equal to 1, a theoretical equation that tells us the relationship between momentum transfer and heat transfer. It has been refined to the so-called Chilton-Colburn analogy. It's valid for flat plate only, but for a larger range of Prandtl numbers. Let's look at an example. Let's suppose, yep. I beg your pardon?
The textbook it says the PDX is equal to 0.
What is equal to TDX?
The PDX there.
The PDX, no, I think if you read on the second page, it actually says it doesn't have to be equal to 0, so you can just check it. Okay. Or close to 0, but in general, flat plates and things like aeroplane wings, etc., this equation would be valid for. Let's suppose with your research project, you are given the task of one or other aeroplane wing or something quite flat. Okay. And it is a heat transfer professor, and he tells you, I would like to know if the air flows over this flat plate and it's at a temperature of 20 degrees Celsius and 7 meters per second, what would the heat transfer coefficients be? Okay, now let me put it here. So there it is. And its length is 3 meters. 3 meters. And you have to determine what is the heat transfer coefficient going to be. So normally, most people, the reaction would be, okay, I need the heat transfer coefficient. So from fundamentals, I can say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the area, and then the temperature of the surface minus T infinite. And then you would think of this plate and you would say, right, how can I get some heat transfer in it? So most probably I will put in an electrical wire there or an electrical resistance element, and I would put a heat flux through it, which I can measure, the voltage drop and the amperes, so that I can get this term. I can go and measure the fluid temperature, the surface temperature, and that temperature is 20. And then I can get the heat transfer coefficient. You agree? So that is typically an experiment that can be done. However, let's suppose you are being told that no, you're not allowed to take any temperature measurements and you are not allowed to do any heating. How do you get the heat transfer coefficient? Well, the Reynolds analogy tells us this wonderful thing, and that is that in nature, if we know what the forces are, then we can also get the heat transfer characteristic. So how can you do it? You put a scale there and something like that, and you'll hang it up. And on the scale, most probably, let's suppose the force would be 10 newtons. The mass multiplied by the gravity. Okay, that is then before you put on the fan that gives a velocity of 7 meters per second, and after you've put it on, it is going to be 10.86 newtons. You know that the drag force is equal to the skin friction coefficient multiplied by the surface area multiplied by rho v squared divided by 2. Okay, the drag force would be equal to 0.86 newtons because before the time it showed 10 newtons because of the weight of the plate. When you put on the fan, that gives you 7 meters per second of flow over it. It's going to give you 10.86, so that is before and after. So the drag force because of the flow is going to be 0.86 newtons. It's going to be equal to CF multiplied by the plate, and let's suppose it is 1 meter in that direction, like that. 1 in that direction. Sorry, no, it's 2 meters. 2 multiplied by 3. So the area is 2 times 3, 6 square meters. However, in this case, the flow is going to be on both sides of the plate. So it's multiplied by 2 to make provision for both sides of the plate. It's equal to the density. Let's suppose the density of the air is 1. The velocity is 7 meters per second divided by 2. And from it, we can get that the skin friction coefficient is going to be equal to 0.00243. The Reynolds analogy tells us that the heat transfer coefficient is equal to CF multiplied by rho VCP divided by 2 times Prandtl to the 2/3. If you don't see this equation here, it is just one of the equations that follows directly from one of these equations. It's in the textbook. So you can go and put in the value of CF, which is 0.00243, multiplied by the density is 1, the velocity is 7, CP of air is 1007, divided by 2 times the Prandtl number of air, which is equal to Prandtl number of air is 0.7309 at 20 degrees Celsius. And that would give us a heat transfer coefficient of 12.7 watts per square meter degrees Celsius. So, without taking a single temperature measurements or determining the heat transfer rate, you can determine the heat transfer coefficient, what it will be. Okay? Now, as I've said, I think that this equation is being underestimated by many people, and therefore in many of the textbooks you would typically get this, but not much more. So the question is now, let's suppose you would like to know in a circular tube. You've got flow through a tube, and we are going to consider that quite a lot. because it represents the most simplest type of heat exchanger available. What do you do now? Because it's a tube, it is not a flat plate. Well, experiments for a tube has been done by a PhD student of mine, Marlies Everts, and we have published it this year, and it was published this year. But it actually shows, here you can see the friction factors, and here you can see the J factors. So you can see how similar they behave in the laminar flow regime in this area, and in the turbulent flow regime, and even in the transitional flow regime. Do you see it? You will, however, see that there are two lines here. What's the reason for that? That is because of buoyancy effects. I'm going to discuss that later. But in any case, if you look at the ratio of F divided by J, you would get something like that. And if you go and develop correlations, then you'll see that there's a correlation for laminar flow and there's a correlation for turbulent flow. I didn't include the equation there for transitional flow because we are not going to give a lot of attention to that. So let's look at an example of a tube, flow through a tube, using the same analogy. So for flow through a tube, for laminar flow, F divided by J, and you will see the J is like that. It means the average value. The average J, it is not at a specific point, is equal to 109.7 multiplied by the Grashof number to the power of 0.215, and it is the Grashof number based on the bulk temperature. Now, what is this Grashof number? We're going to consider it later, but that gives us an indication of the buoyancy effects because of natural convection. What is natural convection again? It is when I heat a surface, this surface is being heated, then this air is at a lower temperature, it will make contact with the plate, it will be heated, and its density would decrease, and because of that, there will be local flow currents close to the wall. And that can be described by the Grashof number, which is equal to G multiplied by beta, the temperature difference multiplied by the diameter to the third, divided by the kinematic viscosity squared. So that's the Grashof number, and we're going to consider that later in chapter 9, natural convection. Okay, so that's for laminar flow, and for turbulent flow, it is F divided by J is equal to 3.74 multiplied by the Reynolds number based on bulk minus 8077 divided by the Reynolds bulk minus 2320 multiplied by Prandtl bulk to the 0.42. And these equations would be valid for a constant heat flux. We will later on look at why that is important. You'll see that normally in laminar flow there are two different boundary conditions, and that can be a constant heat flux or a constant wall temperature. We will come back to that later on. Okay, so those are the equations that we've recently published. The one for laminar flow, which at this stage you are not really ready to use because of the Grashof number, which we will discuss later on. But here's the one for turbulent flow, and at this stage you've got all the tools to actually be able to use that. Let's do an example. This example is going to be flow through a tube. It's going to be water at a temperature, inlet temperature of 19 degrees Celsius. The velocity is 0.7 meters per second. The outlet temperature is equal to 21 degrees Celsius. The length of the tube is equal to 8 meters, and the tube diameter is 11.52 millimeters, almost a half-inch tube. And the tube is being heated at a constant heat flux. Okay. And now, take note, everything that has been given are either properties, or you can get it from the tables, geometrical information, the length and the tube diameter, and temperatures. So in general, it is heat transfer data. But the question is, determine the pressure drop over the tube. Determine the pressure drop. You all follow that? The tube, length 8 meters, diameter, internal diameter 11.52. Water flows in it at 19 degrees Celsius, a velocity of 0.7 meters per second, average velocity, and the outlet temperature is 21 degrees Celsius. So all that has been given are the geometries, the geometry details, the length and the diameter, the temperatures, the velocities and stuff like that, and the properties. And the question is, determine the the pressure drop of this tube. Why would that be important? Because we need to know what the size must be of the pump that we must connect to this heat exchanger. Right. Now the bulk temperature would be the average of the inlet temperature and the outlet temperature, which is 20 degrees Celsius. That is the bulk temperature. Why is that important? It is important because here you can see we need the properties at that bulk temperature. So at that temperature we need the viscosities, the CP values and the K values, etc. So from table A9 in your textbook, you can determine that the density at 20 degrees Celsius is 998 kilograms per cubic meters. The viscosity is equal to 1002 multiplied by 10 to the minus 3 kilograms per meter second. The Prandtl number is equal to 7.01. The CP value is equal to 4182 joules per kilogram Kelvin. The K value is equal to 0.598 watts per meter Kelvin, and beta is equal to 0.195 multiplied by 10, I think is to the minus 3, 1 divided by Kelvin. Beta is the volume expansion coefficient. You can also get it from your textbook, and again we will discuss that in detail when we get to the chapter on natural convection. So, at the temperature of the average temperature between in and outlet, which we call the bulk temperature, which is 20 degrees Celsius, you can go and get in table A9 all the properties of water. Right, Now that we've got the properties, we can calculate the mass flow rate, which is equal to rho v multiplied by the area. The density is 998, so the velocity is equal to 0.7. The cross-sectional area is pi divided by 4, 0.01152 squared, and that is equal to 0.0728 kilograms per second. The mass flow rate is equal to rho, the velocity, multiplied by the cross-sectional area through which the water flows. 998 multiplied by the velocity 0.7, the cross-sectional area pi divided by 4, multiplied by the diameter square, and that is equal to 0.0728 kilograms per second. If we've got the mass flow rate, then it is very easy to determine the heat transfer rate. The heat transfer rate is equal to mCp multiplied by the temperature difference between the outlet and the inlet. The mass flow rate we have determined just now is equal to 0.0728 multiplied by Cp, which is 4182, multiplied by the outlet temperature is 21, minus the inlet temperature, which is 19, and the result is a heat transfer rate of 609 watts. 609 watts. Something that we're going to work a lot with is the heat flux, so let's start using it. The heat flux is equal to the heat transfer rate divided by the surface area through which the heat transfer occurs, so that is around the perimeter of the tube multiplied by its length. So that is equal to 609 divided by pi, the diameter 0.01152 multiplied by the length is 8 meters, and the heat flux is 2103.5 watts per square meter. The Reynolds number is equal to the density multiplied by the velocity divided by the diameter divided by the viscosity. The density is 998, the velocity is 0.7, the diameter is 0.01152 divided by the viscosity, which is 1.002 multiplied by 10 to the minus 3, and that is equal to a Reynolds number of 8031.8, which means the flow is turbulent. For a circular tube, transition between laminar and flow and turbulent flow occurs at a Reynolds number of approximately 2100 to 2300. It's much larger, so the flow is turbulent. Okay, so then we can make use of the equation of Everts and Meyer. Take note, because the flow is turbulent, because it's turbulent, this is the equation to be used, not the one for laminar flow. And it says that the friction factor divided by the J factor. Before I do that, let me just calculate the J factor. Okay, so the J factor by definition is equal to the Nusselt number divided by the Reynolds Prandtl to the 2/3. No, 1/3, sorry. Okay. In terms of the heat flux is equal to the heat transfer coefficient multiplied by the surface temperature minus the bulk temperature. Okay, so I see that I've missed calculating the Nusselt number and the heat transfer coefficient. Just going to do the calculations at home. Okay. And then if you go and look at the Everts and Meyer equation, it gives you F divided by J is equal to 3.74 Reynolds minus 8066 divided by Reynolds minus 2320 multiplied by Prandtl bulk to the 0.42. Go and do that, it is equal to 8.716. Okay, and the J factor you can get from there. As I've said, I've missed calculating it in terms of the specific values. But if you then go through it, you'll get that the friction factor is equal to 0.03399. And to check that, there are three methods that you can go and use. You can go and look on your Moody chart at the Reynolds number to get that friction factor. The Moody chart will give you approximately 0.032. Remember, you cannot really check it that accurately with the second digit, but approximately 0.032. Then there's the Blasius equation that will give it to you more accurately, which is 0.033. And then lastly, the Petikov one, which gives a value of 0.0335. So you can see it is very accurate in terms of these values. And then you can go and determine the pressure drop, which is equal to F multiplied by L of D multiplied by rho V squared divided by 2. Friction factor is equal to 0.03399. The length of the tube is 8 meters divided by the diameter, 0.01152, multiplied by the density, which is 998. The velocity, 0.7 squared divided by 2. And the result is a pressure drop of 57.71 pascals. Okay? Okay, I just want to remind you, in all these calculations, I've unfortunately missed calculating the J factor and the heat transfer coefficient and the Nusselt number. You can just go and do it at home. The principle is, once you've done that, you can put it in that equation and you can get the friction factor. So, what is the bottom line again? The bottom line is, nature tells you, and unfortunately all the correlations is in many cases not available. But if you've got any heat exchanger, if you would, by pressure drop measurements, just go and determine what the pressure drop is, you should be able to calculate the heat transfer rate. Or if you know what the heat transfer is, you should be able to determine the pressure drop. Any questions? If not, thank you very much.